Right. So previously we are familiar with at least the lattice vibration of one-dimensional monatomic lattice, that is only single type of atom that are present in the crystal. But consider some example where there are two kinds of atom, or those atoms have different masses. Okay. In this figure, you can see here that this in this figure there are two types of mass point. One is designated by this blue round circle. Okay, and those blue round circle, they are having mass m2, and there are another type of atoms. Those are black in black circle, and these atoms are having m1 masses. So you are having two types of atoms. One is of M1 mass and another is of M2 mass. And in such situation happens in many cases, like the sodium chloride, like cesium chloride. In those crystals, we can see that uh, there are the masses of different although the different ions have different masses, and they are not same like the monatomic lattice point. And we are assuming, uh, as we have assumed in case of one-dimensional monatomic lattice, that those mass points are basically connected by some invisible spring. Okay, and those invisible springs are basically uh, represent the bonding between any two lattice point, or I can say the force between two lattice point, and those springs, according to our assumption, having the force constant of beta, right? Now, if you consider the sodium chloride crystal, this is obviously face-centered cubic structure, and if you look for the plane of 111, you are getting same types of atoms in that 111 plane. And for cesium chloride, obviously in 100 plane, you are getting the same types of atoms. So we consider the vibration in those planes, but at the same time, we are not focused, we are not considering the vibration of those atoms which are connected along this direction, this perpendicular to the plane, and obviously along this direction, which is the another direction of this. So we are considering only the one-dimensional diatomic lattice vibration in this point. Now, what happens that when some vibrations are arising in this particular situation, and those mass points, that M1 and M2, they are vibrating with according from their mean position. So this first position, which I represent here, is the equilibrium position where no vibration is present. So this state is basically the freezing state of this diatomic lattice, one dimension. But when some kind of simple harmonic motion that are present in this crystal structure, those mass points, they are basically shift from their mean equilibrium position. And for our simplicity, we are considering that those mass points who is present at this even position, that means 2n, 2n plus 2, 2n plus 4 in the left hand side, 2n minus 2, 2n minus 4, those mass points have having mass m2, and they are evenly spaced mass point. But those mass points which are having mass m1, they are basically odd position atom, and those are having mass m1. So in this particular example, for for sodium chloride, we can consider the sodium ion with this black and this chlorine ion with this blue. And for cesium chloride, we can consider the cesium along with this black point, or chlorine along this blue. So we are having freedom in our hand. We can choose any option, either blue or the black. But the situation becomes the same. So some kind of vibration, and those atoms are vibrating in simple harmonic motion, and they are basically shifted from their equilibrium position. Now, if you consider any particular atom, so we are considering this M2 atom. So what happens for M2 atom? This M2 atom have their neighboring atom in right hand side, this is M1, and this left hand side, this is M1. So when this M2 atom is displaced from their main position, what happens? This spring will either elongate or compressed, and on the other hand, this spring also is either elongate or compressed along according to the direction of displacement of this M2 atom, right? So if this M2 atom is displaced, this displacement must be dependent on, or the force on this M2 atom due to the shift from its equilibrium position is basically influenced by the shifting of its neighboring two atoms having mass M1. So right, so I want to say that if you consider this M2 atom, its vibration is or the force of this M2 atom due to simple harmonic motion is responsible for the shift of this M1 atom in both sides. So this situation happens not only for M2 atom, for any kind of atom which are present in this chain. Okay, now as you can see here, there are two different mass points, right? One is M1, another is M2. Now any vibration that are propagating through this lattice point, they might not be have same amplitude for this M2 or M1, or I can rather say that this M1 atom is vibrating with a particular amplitude, but this M2 atom doesn't have that same amplitude of vibration, as these mass points are different. So as M1 and M2 are different, so it is quite obvious that they are not vibrating with the same frequency, frequency amplitude, right? But the frequency of vibration we are yet to calculate, assuming the simple harmonic nature of this particular situation. Now, what you will see here, so I just remove this point, and one thing you keep in mind that any particular same atoms, either this M2 or M1, they are separated by this square distance, and the different type of atoms, that is M1 and M2, they are separated by a distance, right? So this is the particular situation of this two-dimensional diatomic lattice point. Now, once if you consider this situation, and I am going to the detailed analysis of the particular simple harmonic vibration that are present for this type of lattice point, and we are going to generate some what should I say, equation of motion, and from that equation of motion we are going to calculate the frequency of oscillation of this particular situation, and let's see what happens when you have the two types of different mass point they are vibrating in at the same time with some vibration. Okay, so let us start with the mathematical part of this vibration. And as you see here, that in my previous class, I have already told you that even there is absolute zero temperature, there might be some vibration due to thermal vibration obviously, and at zero temperature there will be some 0 point energy, so there must be some vibration present in the lattice point. So if you have two atoms in lattice point, and once you consider that the odd lattice have the what should I say, mass in one, and the even lattice point having mass in two. And according to that, this odd lattice point, they are basically 2n plus 1, 2n plus 3, 2n minus 1, 2n minus 3. So these are the position of those points, and at the same time, this even atom has twice n plus 2, 2n plus 4, 2n minus 2, 2n plus minus 4. These are the position of even atoms. And obviously, when we are going to calculate the simple harmonic motion, we are assuming that x 2n plus 1 is the displacement of all atoms from equilibrium position, 2n minus 1, x 2n plus 3, x 2n minus 1, x 2n minus 3, and such that. So this displacement is suffixed by these odd numbers, and this displacement is obviously x and suffixed by this even number. So x2n is the displacement of 2nth atom, x2n plus 2 is the displacement of 2n plus nth atom, x2n plus 4, and such way. We are considering that these are the displacement from equilibrium position of any particular lattice point. Now, at first, we are going to deduce the equation of motion of this lattice point. So, what happens when we are considering that is the force? So, see here, this lattice point has V1, and it is spring with lattice point M2, and at the right side, this is M2. Okay, now these lattice points are having x twin amount displacement from equilibrium position. These lattice points have this is M2n plus 1. So this M2, which as M1 is hot, so this M2 having this 2n, and this is x 2n plus 2. So these are the situation for when you consider this odd atom present here. So the relative displacement between these two, that is how much the spring will be either compressed or elongated, is given by this factor, that is x 2n plus 1 minus x 2n. And at the same time, this spring will be either compressed or elongated by x 2n plus 1 minus this x 2n plus 2. So these are the compression or rarefication of these two spring in two different directions. And as you see here, if F1 is force that is arising due to spring compression of this one, and F2 is the force arising due to spring compression of this 2. So F will be F1 plus F2. Simple vector sum, because it is along the same direction. So as the vibration is along the same direction, so force is along the same direction, we can just simply add up them. So as this M, the displacement of this x2n plus 1 atom, due to that particular displacement, as this atom is feeling some kind of force, some restoring force, and that particular restoring force is trying to move that particular M1 atom to its equilibrium position. So as that restoring force, according to D'Alembert principle, I can write that this restoring force will be M1 d square x 2n plus 1 by dt square. So this is the acceleration, and the force obviously on 2n plus 1 atom, and this force is basically the relative displacement between 2 points, and obviously this force is minus spring constant, obviously x 2n plus 1 minus x 2n plus 2 minus beta x 2n plus 1 minus x 2n. Right? So this equation becomes minus beta x 2n plus 1 twice minus x 2n plus 2 minus x 2n. So particularly I can write here by eliminating this minus sign. So this will be beta x 2n plus 2 plus x 2n minus 2 x 2n plus 1. This 2n plus 1, 2n plus 2, 2n are just the suffix of this xn. Right? Now, this basically the equation number 1, and the same thing happens when you are considering for these even atoms they are present here. So if there is some even atom and its mass is obviously M2, so this is M1, this is M1. So even atom, let us consider the displacement is x2n. So in the right hand side, the displacement 2n plus 1, and this will be 2n minus 1, right? So at the same time, the same thing happens for this particular case, and we will get the second equation, that is force on 2nth atom having mass m2. This is basically m2 d square x2n by dt square. This will be beta x 2n plus 1 plus x 2n minus 1 minus 2x square. So these are basically the two equations. This is equation number 2, and first I have written the equation number 1, and once again I am going to write that is f 2n plus 1 is equal to m1 d2 x 2n plus 1 by dt square. This is equal to beta x 2n plus 2 plus x 2n minus 2x 2n plus 2. So this is equation number 1. Okay, so we are having two different force equation for two different type of atoms in my hand, and I am going to deduce the mathematical derivation of this equation. Now, if you consider that two mass points having different mass, so first I have to consider that this M1 is not equal to M2, as this n1 is not equal to n2, so these two vibration or the amplitude of these two vibration might not be same. And if this might not be same, the even atoms having mass m2, they are vibrating with the amplitude eta, and the odd atom having mass m1, they are vibrating with amplitude, sorry, this will be psi. Okay, so eta and psi are basically two types of vibration of these two atoms. Now, when we are considering the vibration of even atoms, so the even atoms basically are 2n, 2n plus 2, 2n plus 4, 2n minus 2, 2n minus 4. We are considering this amplitude. And when we are considering the odd atoms are vibrating, we are considering that 2n plus 1, 2n plus 3, 2n plus 1, 2n minus 1, 2n minus 3, etc. So these atoms are vibrating with this psi amplitude. Okay, so as this happens, I can assume that my trial solution for this kind of vibration must be a simple harmonic motion, or I can consider that, as we can consider in case of monatomic lattice, that x2n will be eta times, which is the amplitude, and some phase part that are related with this amplitude, that is exponential, obviously I, which is imaginary, root over minus 1, omega t minus 2k in A, as this two same lattice point, they are separated by 2a distance. So basically k n into a, n is the order number and 2a is the separation of each individual lattice point having same type. Okay, now for odd atoms, that means x2n plus 1, we are considering psi is the amplitude. So psi exponential I, which is omega t minus 2, as this is 2n plus 1 at atom. So this will be 2n plus 1 k. Right? So we are using this two equation, I equals to root over minus 1 here, and now we are going to replace these two particular trial solution, because this is basically trial solution in this particular situation, and to calculate the omega. Okay, and we are going to calculate how many omegas are present in this particular case when the system having different mass points, right? So once I put this equation, this form in first equation, we are just removing all these things and we are going to put these things here. What we will get? We will get that the situation is like, if you differentiate x2n divided by dt square, so this will be minus obviously omega square beta exponential I. This will be omega t minus 2k in a, and at the same time, if you put some odd point here, so there is some light in here, so this will be omega square beta exponential exp within the third bracket I omega t minus 2k in a first bracket from the third. Okay, right? So this is exponential, right? This is exponential basically, and within the bracket this is I omega t minus 2k in a. And obviously d2x2n plus 1 by dt square. If you consider the odd vibration, so this will be minus omega square by exponential I omega t minus what I will get, that 2 in plus 1 in, right? Now, if you consider the relation between two individual displacement, one is x 2n plus 2 and another obviously x2n. So the ratio of this x2n plus 2 and x2n will be exponential minus I obviously 2a. And this x 2n minus 1, this will be x 2n plus 1 and exponential I 2a, right? Okay, now I am going to just replace all this term in first equation, and what I will get. So from first equation, that is the equation of even atoms, that is just this equation, and then up top hand side writing this equation d2 m2 d2x2n dt square. This will be beta x2n plus 1 plus x2n minus 1 minus 2x2n. So if you replace those particular things which I have just derived in here, you will get that minus m2 omega square, this obviously beta exponential I omega t minus 2 kNA. This will be equal to beta times what we will get, that is basically as this is odd, so this will be xi exponential I omega t minus 2n, as this is 2n plus 1, so this will be 2n plus 1 Ka plus xi exponential I omega t minus 2n minus 1 Ka minus 2. This is x2n, so this will be beta exponential I omega t minus 2n A. Right? So for sake of simplicity, I can write this 2n A here. Okay. So you will get this equation first. So if you just remove this term, what you will get? In here, you are having, if you remove all this term, you are having just, this is 2nk, so minus I k p here. Now if you remove this term, what you will get? This will be plus I k p. And this term is completely removed. So if you just divide this exponential I omega t minus 2 nka in right hand side, so this term will disappear and this term will disappear. In this case, you will just having exponential minus IKA in the term just here. Once again, you will have exponential IKA and this will be removed and you will get just this. So by applying, I am writing this term once again here and we will get beta xi exponential IKA here minus exponential minus IK plus exponential IKA minus 2 eta. Okay. So from this equation, if you just bring the whole thing in left hand side, what you will get? This will be 2 beta beta. So 2 beta minus m omega square eta minus, this will be beta xi exponential minus ik plus exponential plus ik. This will be, this whole thing will be 2 cos ka. As you see here, cos I e to the power I theta, this will be cos theta plus I sin theta, and to the power minus I theta equal to cos theta minus I sin theta. So this will be just 2 cos ka. So this will be 2 beta xi cos ka. This will be 0. So we are getting the first relation between this omega and k from here, right? Now when you consider the vibration of odd atoms, what you will get? So if you consider the vibration of odd atoms, so when you consider the vibration of odd atoms, you will get the vibration of all atom, and the equation of motion first I have to write. So m1 d2 x 2n plus 1 by dt square. As there is light in here, I am writing this equation down, downward. So beta x 2n plus 2 plus x 2n minus 2x 2n plus 1. Right? Now if you replace all this term here, as I have written in case of this equation, to derive this equation, what you will get? In the left hand side, you will get from this equation, in the left hand side, you will get just minus m1 omega square. As this is odd atom, so the vibration will be psi, amplitude will be psi, exponential I omega t minus 2n plus 1 AA equals to beta times, this will be x2n plus 2. So this will be exponential I omega t minus, as this is 2n plus 2 here, so 2n plus 2 AA plus exponential I omega t 2n AA, as this is 2n, and obviously here this is minus, so minus twice beta, and this is odd vibration, so this will be this the amplitude will be eta here, amplitude once again will be eta here, and the amplitude in this case will be psi here, right? So as this is even vibration, so amplitude will be eta. This is even vibration, amplitude will be eta, and this is odd vibration, amplitude will be psi. So psi exponential, what you will get here, I omega t minus 2n plus 1 A. Right. Okay. So in that particular way, which I write in previous case, we just wipe out this term or divide this term in the right hand side. From here you will get minus ik. From here you will get just plus ik, and this term will be eliminated. So from this equation, if you just wipe out this term, divide this term in the right hand side, you will get eta exponential minus ik, and in this case we will get just eta exponential plus ik, right, within the bracket, and we will get this. So from this equation, from this particular equation, if you write another relation, what you will get, if you bring this term at left hand side, we will get 2 beta minus m1 omega square into psi minus eta. If you just make it out from this as a count factor, so exponential minus ik, exponential plus ik, add them, what you will get? Obviously 2 beta eta cos EA discussed to see. Right? So we are getting two types of solution, one is having its M1 mass and another having M2 mass. Now we just have to derive the solution. So as these two equations, we are having these two equations. If these two equations are having non-zero trivial solution, if these two equations have non-zero trivial solution of this eta and psi, amplitude of this eta and psi amplitude, the determinant of the coefficient of eta and psi must be equals to 0. Okay, so if that particular thing happens, then the coefficient of this eta and psi from these two equations will be 0. So if you reduce the determinant, what you will get from first equation, if you write, this is 2 beta minus into omega square, and this will be minus 2 beta cos Ka, and from second equation this will be minus 2 beta cos Ka, and this will be 2 beta minus omega square. For non-trivial solution, non-zero trivial solution, determinant must be equal to 0. Okay, so as we get the determinant is equal to 0, now I have to just simplify them and solve this equation to get the values of this omega. So first, simplify this equation, and what you will get, that 2 beta minus m1 m2 omega square into 2 beta minus m1 omega square, and this two term again minus 2 beta cos Ka and 2 beta cos Ka is equals to 0. Right? So from this determinant I can get this. Okay. Now just multiply them. What you will get? You will get just m1 m2 omega to the power 4. Right? Minus 2 beta omega square m1 plus m2. Okay, so what we will get, just 2 beta omega square m1 plus m2 plus, here this will be 2 beta into 2 beta, so 4 beta square minus here 4 beta square cos square Ka equals to 0. Okay, so if you, from this two equation, if you just make 4 beta square common, this will be cos square Ka, so this will be 4 beta square sin square Ka. So I just replace the whole term by 4 beta square sin square Ka here. So this equation will be 4 beta square sin square Ka. And now this is a quadratic equation of omega square. Okay, So this is basically a quadratic equation of omega square. And as this is the quadratic equation of this omega square, so you will just solve this equation to get the quadratic equation. So let us first see what is the solution of any quadratic equation. So let us consider a quadratic equation having ax square plus bx plus c equals to 0, and the solution we are applying this Sridharacharyya rule, and we will get minus b plus minus root over b square minus 4ac divided by twice a. So you are getting just this solution. So from this equation, what will be the values of this omega square? So if you consider this omega square, and this omega square will be minus b, so this will be minus of minus 2 beta omega 2 beta. This is m1 plus m2, right? Plus minus root over b square, that means minus 2 beta into m1 plus m2 square minus 4ac, 4a into c. So 4 times m1 m2 multiplied by this 4 beta square sine square ka. The whole thing is divided by just 2 m1. Right. So if you divide the whole thing by 2m1 m2, you will get and for as this omega having two values, so I am writing this as plus minus. For omega plus we are choosing this plus sign, for omega minus we are choosing this minus sign, right? So for omega plus minus, what we will get here, so omega plus minus, this will be twice beta m1 plus m2 divided by 2 m1 m2, just 2 is removed, so this will be m1 m2 plus minus root over, so this will be 2 beta square. So if you just remove this 2 will be removed. So you just bring this m1 m2 in this point here within this bracket, and you will get this as beta m1 plus m2 square divided by m1 m2 square, right? Minus, if you bring this 2 within this bracket, you will get 4 and m1 m2 here, so this will be 4 m1 square into square. So this will be 4 beta square sine square Ka divided by just m1. Okay, so you were having just two types of frequency. One is omega plus and another is omega minus here. Okay, so two angular frequencies are present in this case. Now the frequency with omega plus are having term beta m1 plus m2 by m1 m2 plus beta m1 plus m2 divided by m1 m2 square minus 4 beta square sine square Ka divided by m1 m2 to the power half. This frequency or this mode of vibration is basically called the optical vibration or mode. So this omega plus is basically the optical mode of vibration, right? On the other hand, this omega minus, this will be beta m1 plus m2 divided by m1 m2 minus beta m1 plus m2 divided by m1 m2 whole square minus 4 beta square sine square Ka by m1 into the power half. And this omega minus is called acoustic vibration mode. Now, what are the basically the characteristics, or why should I call this two term as one says optical mode, another is acoustic mode? So let us consider these two atoms are vibrating in a particular situation. Okay, this black one having m1 mass and this blue one having m2 mass. So once they are, if I put this whole these two things in crystal lattice, and they are going to vibrate in two different times. What is that? One, this is vibrating along this direction. So the spring between these two just compress, okay, and the direction of vibration is different here. And another type of vibration is along this parallel direction, right? And on the other hand, I can say that this two vibration having this two direction, right, and another vibration having this direction. So the vibration which are along this direction, they are having the same amplitude, okay, and on the other hand, this vibration, they are in just opposite phase to one another. Okay, so once if this vibration of omega plus, the same thing happens when I put this type of vibration, and for acoustic mode we are having either this type of vibration here. So once you just expose the crystal with some optical oscillation, okay, some optical wave are propagating through the crystal or the lattice point of the crystal, they are vibrating with this omega plus mode. And when some acoustic vibration that are basically propagating through the this crystal, the crystal might vibrate through this omega minus oscillation. So simply we are saying that if there exist two types of atoms here, M1 and M2. So if there exist two types of atom, the situation is completely different from monatomic one, and we are getting sorry, this will be must be square here. Sorry, so this must be square here. So from this equation, we are having two types of oscillation. One is just optical mode of vibration, and another is just acoustic mode of vibration. So what we will get that this situation is different from monatomic one. For monatomic one, we are getting just single omega versus k graph, and the graph will be like this: pi by a to minus pi by a. We are having this type of graph, but in this case, this omega plus and omega minus, they are distinctly different. So the situation is completely different, and we are going to discuss this whole thing, that is the frequency spectrum, that is omega versus k graph for diatomic lattice in the next class. And just sorry for this notation, that this will be omega square. I have written previously as wrong, so this will be omega square. So omega plus square, omega minus square. But the thing is that the frequency is basically different. So one is optical mode of vibration, another is acoustic mode of vibration. So with this, I am ending just this part of discussion. In my next class, I am going to discuss the relation between omega and k, and how this graph look like in first Brilliant zone and second Brilliant zone for this diatomic lattice. So thank you for